So we have our particle that is forced to live between x equals 0 and x equals L. And let's say that we have a psi of x and 0, which is unequal weighting of the ground state and the first excited state. So that means that we have 1 over square root of 2 psi 1 of x plus 1 over square root of 2 psi 2 of x. Maybe we should write these out. So this means, well, first of all, let's write the time dependence. Once we know what the wave function is at t equals 0, we can figure out what this is, and that's just 1 over square root of 2 psi 1x e to the minus I e1t over h bar plus and if we write out the full expression, it looks like so. So let's 1 over root 2. All of these functions, all of these eigenfunctions have the same normalization factor, which is root 2 over L, right? The root 2 will cancel, but let's just leave that like that. And then we'll have a sine of pi x over L for the rest of this term, e to the minus e1t over h bar, plus a sine of 2 pi x over L for the rest of this term, e to the minus I e2t over h bar. So now let's consider the probability density, right? So psi equals, p equals psi star psi, and what does that look like? So square root of 2 cancels, we get 1 over L times, right, we have, we're multiplying a term that has these as positive times this term itself, right? Right, this is this, and this one is the one with these things positive. So we get simply this thing squared. We get sine squared of pi x over L plus sine squared of 2 pi x over L plus, we have the two cross terms. We have 2 sine of pi x over L sine of 2 pi x over L. Then we have a term that we know becomes a cosine of the energy difference times t divided by h bar. So we get a term which is cosine of, we have the bracket here, e1 minus e2 t over h bar. And we can consider what this looks like. So let's consider plotting the probability density as a function of x. So here's 0 and here's L. And let's plot it for different times. So at t equals 0, right, we have the cosine, where are we? Cosine of 0, that's just 1. So this whole thing is 1. And so when we plot this, we have a function which is even, right? This function here is just one big bump. It looks like that. And to that, we have to add the square of a function that's also even, but it's, right, so it's going to look like the sine of 2 pi x over L looks like that. It's the odd function. But it becomes even because we square. So we have 2 bumps. And so the sum of these two is an even function in this, with respect to the midpoint of the well, right? So it looks the same on this side as it does on this side. But to that, we have to add this quantity, right? And this quantity is positive on the left half of the well because both, right, we have one half a bump for the sine of pi x over L in this part, and this one contributes a term which is positive like that. It's one bump, one completed bump halfway to L. But on this side, right, although this term gives us the rest of this function, which is also positive, this one gives us a negative bump. So we have a negative term on this side, which subtracts from this. So at t equals 0, the probability density needs to be greater on the left-hand side compared to the right-hand side. In fact, it looks something like, it'll start to die down as we get to the middle of the well, and it will actually have like a little bump and look something like that. That's at t equals 0. And there will be some time when this thing is -1, right? So that sometime when this is -1, then the opposite will happen in the sense that the negative term that we just considered subtracting on this side, which made this lower, now becomes positive because of this term here, because this term is now -1, so that thing becomes positive. And so we add exactly what we have here, what we had initially here, we add that on this side, and so maybe we can make this in a different color with green. So sort of the, I want to rotate this 180 degrees to this side. So I have a, I didn't see how to do this, but yeah, so it's going to be a little bump like this, and I'm going to come down here and come back up like this, and come down like that. So this is some t, I don't know, t equal to t star. We can figure out when the cosine gives us -1, right? This whole thing has to be some fraction of pi. Yeah, it has to be pi, and so we can figure out what the time has to be. The time has to be some multiple or fraction of pi. And so there is an intermediate time. I don't have my red colors, but let me do it. So let me use a yellow. There's an intermediate time when we will have something like this, where we lower it a little bit here, and we come in here and have a even function like that. And this is at a time that's in between these two times. So this is t star over 2. And so we can kind of get a sense that the probability density is oscillating. It's large on one side, and then it's shifting, starts to increase as we move this way. It's lowering here, and it's increasing in other places, and then it shifts to the other side, and then back. And so in some sense, that represents a particle that's moving right and left, back and forth. But that's a little bit deceiving, because other combinations, as we'll see, of eigenfunctions will not produce this kind of behavior.